13.6, parametric surfaces. So we're going to summarize and generalize everything we learned about line integrals to surfaces. We're going to take line integrals and put the two surfaces. How to parametrize a surface. Surfaces are hard to explore because they change all kind of dimensions and they have different sides. So we're going to learn the surface direction. They have inner side and outer side. So we're going to have that positive side and negative side. So I realized I was discussing it with a graduate student, and I told a graduate student, somehow parametrization is hard for students to grasp. What parametrization is even for? You don't have to write this down, but parametrization, I found, is a mathematical process consisting of expressing the state of a system or process or a model as a function of some independent parameter variable. So we learn how to parametrize circles, r cosine theta and r sine theta. Sometimes it's sine t, cosine t, right? That's t is the third independent parameter. Remember, there was parabola parametrization. X equals t, now y is t squared. Why are we doing this? We want to express the state of the system using an independent parameter. So third or fourth variable, any kind of other more dimension, and usually it's time. So the goal is to parametrize a surface, which is hard. The idea is, do you know this little tool for kids when they give you to draw? You have left handle and you have a right handle. So we will be using that or via vectors. The left handle will be vector u. We will be using two vectors. Will be u, and the right handle will be v. U and v, just two vectors. While moving them at the same time, we will be sketching the surface like so. So that's literally how this game works. We're going to be using vectors. So draw this picture above. Here is a surface. Let's say like a piece of paper or a flag. You see, it's a three-dimensional object. We will be describing it using u and v. U goes first, like an x-axis, and v like y-axis. But we're not going to be using x and y. We will be using u and v. S is two-dimensional here, so we need two parameters, u and v. The analog we had before was r of t. Before we had r of t. Remember? Do you remember? And no, you see, nobody ever sings back for some reason. Now we have, right? Now we have r of u and v. My favorite question when we have complicated discussions about theorems between friends, theorems and proofs, and we talk about this, I'm like, I still have a very important question. Like, yes, what is Julia? Like, what is love? And people like, baby, don't hurt me no more. It's like very classical answer. Everyone knows the answer for this question. What is love? Now we're using two parameters, and that's why it will be harder. Like, it's kind of getting messy. Even with one parameter, people struggled, so you can imagine. Example. Parametrize the cylinder. That's it. No parabolas and no circles. We're going to upper dimensions, surfaces. Cylinder has a surface. To parametrize that, we're not going to be using t anymore. We need more dimension than just time. So before, we had two dimensions, and then I remember we had parabola in the homework, right? And it was beautiful parabola like this. Y equals x squared. We used t. It's as example. We chose x to be t, then y became t squared. Parametrization is not unique. Parametrization is a very creative process. And then t was from something to something, and we could choose how far it goes. And that also gave us some kind of direction. Counterclockwise, clockwise, positive, negative. So now this is not enough. Remember, t is like kind of pointing x, y. Where is t? T is independent variable. It's an upper dimension. In this case, third dimension. Now we have 3 dimensions. So we need a 4-dimension variable. No, we need more dimensions. Not just t. We need u and v. cylinder, in cylindrical coordinates, the equation for the cylinder is r equals 2. Why? Because it's a radius. Radius is 2. So we know that cylinder has height, and we're going to be describing height as z. And cylinder have angular rotation. So in this case, it's positive with theta. So we'll be using, instead of like in cylindrical coordinates, we used to have x, y, z. Now we will have theta and z. Theta and z. Remember, there were formulas. X equals r cosine theta, y equals r sine theta, z equals z. So we basically have, if r is fixed, we have only two variables, theta and z. We will call it u and v. You don't have to actually call it u and v, but that's the one. That's the u and v one. So again, let me describe what I just said. We know in cylindrical coordinates, x was r cosine theta, y it was or is r, oh, no space, y is r sine theta, and z is z. That's cylindrical coordinates. Well, r is fixed. It's 2. So we have two variables that keep describing the cylinder. Again, you use those two variables. This is my theta and this is my z, like those two handles over here. Theta, z. And when you move both, the shape of the cylinder is being created. You kind of like, it's a surface. So you go around and around and you go higher because z is growing, and you draw the cylinder like in that toy. So the answer follows. R. No. We're almost done. R depends on theta, the angle, right? And the height of the cylinder. Equals, we plug it in, whatever I just wrote down, 2 cosine theta, 2 sine theta, and z. That is exactly the answer. We just need to figure out theta and z. So that is parametric form with two parameters, theta, comma, and z, which are basically my u and v. Where, and now I just need to define theta and z. Theta is spinning round and round and round. So what is the limits for theta? 0 to pi, exactly. Don't overthink that. Z is going up and down forever. So what is your z? Minus infinity to plus infinity, exactly. Good job. Put this in the box, that's the answer. So the first example was not too bad. The only, I think, confusing part for people, how did I know that? The answer is, I looked in my notes. No. The answer is, you have to choose it. We do know how cylinder is described in Cartesian. And then I noticed that r is not a variable. Theta and z are variables. Like, oh, that's exactly what we need. We need two parameters. So I will use those theta and z as parameters, which are independent variable. Here they are. They rotate and shrink and stretch, and they slowly draw the cylinder going up and down forever. Yes?
So you always like write the parameterized form as kind of x, y, z?
No, that's oh, your question is
Like
yes. This one, yes, like this. So we used to have r of t. Now I have r of u comma v. So that's exactly what we're doing now. We're rewriting it this way in order of alphabet usually. Yes.
So there aren't really any formulas for this one?
No. Remember parametrization in calculus 2, the end, there was no formulas. It's a creative process, which makes it harder. It's always the hard part. We're going to do more examples, and you'll be more flexible with that, more comfortable. Good job, people. Don't get sick.